if you have not covered thermodynamics yet, then well, everyone should at this point. Okay, but I do have some um, Zoom video on some of these topics. I'm just going to go over some of these questions and then make sure that you understand the approach for some of these questions so that you can at least start it correctly. So the first question here is all you're doing is stating whether it's positive, entropy is increasing, or negative, entropy is decreasing, or maybe zero, entropy is not changing. You don't need a numerical value. Okay, that's not what I'm asking for. But if you want to do a numerical value, that's fine too. In fact, if you do a numerical value, that'll probably nail down your answer based on the progress that's going on. So the first reaction here, I'll just do a couple, is water in its gaseous state. Remember when a chemical is in its gaseous state, it's randomly moving around. Remember what entropy is. Entropy is chaos and randomness, but at a more defined level, it has to do with microstates. The more available microstate, the greater the entropy. Okay, that's why a gas has a higher entropy than a solid, because the availability in XYZ space is more available. There's more microstate than the solid, which is sort of fixed in its position. So here we have an example of a water gas going to water liquid. You guys should know that. Here we have C6H6 is a chemical called benzene. It's an organic solvent. It's going from the aqueous, which is in water, to a gas. Okay. Here we have potassium chloride. And remember, potassium plus one, chlorine's -1. And it's going from aqueous to a solid. So just based on what's going on, and you guys should be able to visualize what potassium chloride in water looks like and what potassium chloride in its vapor phase may look like. You should be able to envision whether there's more microstates, there's more chaos in the solid versus the aqueous. Okay, here we have two waters breaking down to two hydrogen gas and oxygen. Okay, here we have two benzene. This is benzene again, same chemicals as this one right here, plus 15 oxygen. And here, notice that this is a combustion reaction. How do you know it's combustion? You guys should know this based on your knowledge in general chemistry. You know it's combustion because look at the products: carbon dioxide, water, and look at the reactant. You need oxygen from there. So no one's going to tell you that this is a type of reaction. You should already know this just based on what species are involved. Okay, so this first part is just determining whether it's positive, entropy is increasing, entropy is decreasing, or there's no change. And if you want, you can do the extra work and look up the entropy and do products minus reactant if you want. Okay, that's not so critical. You really should be able to look at a reaction or a process and just based on instinct, know whether the entropy is increasing or decreasing and whether it's an endothermic or exothermic. Yeah, you probably don't have enough experience to know exactly for a lot of the reactions out there, whether it's endothermic or exothermic, but you know the common ones. You know the common ones, okay, like a combustion reaction or photosynthesis, things like that. So that's that part of the question. The second part of the question is, this is similar to an example that I gave in the lecture notes in chapter 19. Okay, I gave you, especially on the topic on entropy, I gave you a series of chemical and I asked you which one has the greatest entropy. Well, this is a very similar question. Okay, for each row, figure out and explain. You need to explain which species would have the for each table thermodynamics, circle the compound in each row that would have the greatest value of entropy. which one's the most chaos, which one is has the most microstate available. That's all you're doing. Okay, and if you want, you could certainly look up the value, the entropy value, so that you can nail it down. But try and go with your instinct first. And then if you want, you can look it up. So this one's aluminum chloride, sodium chloride, and calcium chloride, all in the solid state. Second one's methane. C3H8 is propane, and C2H6 is, I believe, ethane. These are hydrocarbons, organic chemicals. And then the third series is lithium nitride, lithium oxide, and lithium bromide. Okay, so think about that. Remember that complexity means that the entropy is larger, but also remember that size is also an important factor. The more subatomic particles a chemical has, the more ways of arranging those protons, electrons, and neutrons, the greater the entropy, all things being equal. So again, it's just to expose you guys so you know how to measure or how to compare the entropy values just based on the chemicals you have. So yes, positive means increase, negative means decrease, 0 means no change. So that's all you're doing here. And then in this one, just circle it. This next one, you've got carbon dioxide plus water. Notice the phase going to C6H12O6, that's glucose. That's glucose and oxygen. You guys should know what type of reaction that is. I'm not going to tell you that. Okay. The energetics here are not there, but if you know what this reaction is, it's a very common reaction, then you know whether it's endothermic or exothermic. Now, this is the balance equation. Calculate free energy for the reaction using standard state conditions, using delta G equals delta H minus T delta S. So that means that you have to write this whole reaction, find out delta H at standard state, delta S at standard state, and then calculate delta G from that equation. I need to see the work on that. Make sure that you show me the work, but put your answer in the activity sheet. Okay. So it's a tedious problem, yes, because you have to look up all those values, but that's what thermodynamics is. Rather have something more tedious than really complex. These are tedious problems. Is the above reaction spontaneous in the forward direction under standard state conditions? How do you know? Well, free energy tells you that. Okay, free energy answers whether it's spontaneous or not. The sign of delta G tells you that. Remember, delta S of the universe increasing is always spontaneous. Delta S of the universe is related to free energy. Free energy of the system is equal to minus T delta S of the universe. So keep that in mind. So that's how you would answer this question. The next question here, the following reaction for the production of hydrogen cyanide is the function of temperature. So this reaction right here, the one that's below, so you're producing hydrogen cyanide. That's this chemical right here. You're forming hydrogen cyanide from ammonia, methane, and oxygen. Okay, and it's temperature dependent. Calculate the free energy at 100 degrees and 500 degrees. Is the reaction more spontaneous at high temperature or low temperature? So remember that delta G, if you try to look that up in the appendix, that's under standard state conditions. In order to calculate delta G at 100 and 500, you've got to use this equation. You've got to use this equation. Yeah, you're using enthalpy at standard state and entropy at standard state, but the T now allows you to convert the free energy at that temperature. So you're going to have to use delta H minus T delta S for this. So that means there's there's really just one set of questions. Once you find delta H and delta S in products minus reactant, then you just have to multiply delta S by the temperature. Remember, temperature is in absolute temperature. It has to be in Kelvin. Don't forget to make that conversion. Otherwise, you're going to be off. And then don't forget what I asked you to do in lecture. The units for entropy is in joules. The units for free energy, that's delta G, and enthalpy, that's delta H, are in kilojoules. If you're going to tie in enthalpy to entropy, they have to have the same units. If they do not have the same units, you may be doing the process correctly, you're going to get the wrong answer. Okay, make sure that the units are consistent. That's why it's always good practice in science to write the units. So this part, not very complicated, just a lot of tedious work. Just a lot of tedious work, okay? The next part right here, more tedious work, okay? There are 4 reactions here. So that means you got to get delta H for the reaction, delta S for the reaction, and delta G from the reaction, okay? And you can determine delta G from the reaction by 2 methods, delta H minus d delta S, or delta G via products minus reactant. You should do both just for practice and see whether or not they're similar to each other. To really streamline this, if you use an Excel spreadsheet, then you can let the Excel spreadsheet do the calculation for you. Plus, it's good practice. But if you don't want to go through the tedium of using an Excel spreadsheet, then just look up those values, make sure it's arranged correctly. The problem when doing a lot of these types of questions is that you lose track of the numbers. And once you lose track of the numbers, then you're adding and subtracting the wrong chemicals to each other, or the wrong state functions to each other. If you're orderly like an accountant, then things will not be confusing. That's the key in a lot of thermodynamic problems, is you got to keep track of the values and which chemical owns those values. You got to be organized. Otherwise, the problems are easy. Okay, the problems are not difficult. Which of the above is exothermic? Which of the above reaction is our exothermic? Remember, exothermics are based on delta H. Which of the above reactions is spontaneous under standard conditions? Remember, spontaneity is addressed by free energy. Okay, so that's what you're looking for. Which of the above reaction could be made spontaneous by increasing the temperature of the reaction? Calculate the temperature necessary to make that reaction change. So we covered this in the last chapter, or the last lecture. And in that last lecture, I think I did this. Remember the equation, delta H minus T delta S equals delta G. Okay, these are delta, so let me change that real quick in terms of the font so that it's easy to see that. Oops, wrong font. Trying to find my symbol font here. So hold on while I change that font to symbol, and then you guys can see how it plays out. So, okay. Okay, there. So that's delta H, this is delta T, delta S, and this is delta G. Okay, now remember that when, I'm just going to do a couple of examples. If this is positive and delta S is positive or negative, for example, so delta S here is negative. Okay, the negative here and the negative here will make this quantity positive. So if you've got an endothermic reaction and you've got a reaction in which the entropy decreases it's never spontaneous, because a positive and a positive will always make delta G positive. Don't bother. You can certainly look at these values over here to make that comparison. But what you need to remember is that when when enthalpy and entropy have opposite sign, it's either going to be spontaneous under all conditions or non-spontaneous under all conditions. It's when they have the same sign that they become temperature dependent. If both are positive, then what happens is that it's endothermic in one direction, for example, but entropy is increasing. The entropy increasing is favorable. The endothermic process is not favorable. The one that wins out is going to be dependent on which of these delta H or T delta S is bigger. And how does this term get bigger? Get bigger because entropy is always constant by T. Okay, when T becomes larger, then this term becomes more significant. Then that term will become more negative. So you have to think about it in those terms. Okay, so this is a really good example in understanding the temperature dependency of the thermodynamic parameters. Okay, that's what this question's about, is do you understand how the temperature influences the sign of delta G based on the value of delta H and delta S? It's not difficult once you understand how these equations operate in their mathematical sense. Like I said about Chemistry 201, Chemistry 201, there's a lot of math. And the math speaks to the chemistry or the process that's going on. And this is a classic example. So that's what this question is. Which of the above reaction is spontaneous under standard state conditions? How do you know? This whole thing actually refers to the bottom here. Which of the above reaction could be spontaneous by increasing the temperature? So the delta G becomes more negative at higher temperature, in other words. Okay, calculate the temperature necessary to make that reaction spontaneous. So remember, if you're in my lecture, that's the switching temperature. The switching temperature is when this is equal to 0, and now you can solve for T. That's the equilibrium process. So these problems are not difficult because you're dealing with simple equations. And then finally, this last two questions right here are about the same thing. Which of the above reaction will always be spontaneous, no matter what the temperature? Why? You need to talk about that. Which of the above reactions become non-spontaneous by increasing the temperature? Again, same discussion here. But that basically is your activity. It's a good activity that wraps up thermodynamics with what we learned in chapter 18. Okay, it's tedious in some places, but it's really good practice for you guys to get a hold of and understand the concepts of delta G and delta H and delta S. Now, the only thing that's lacking in these problems right here is the relationship between free energy and K equilibrium. You guys will see that in the electrochemistry activity, because once we finish electrochemistry, what you will see is that not only is delta G related to free energy, K equilibrium, but free energy is also related to electrochemical potential, which means the electrochemical potential is related to K equilibrium. Okay, so in the electrochemistry activity, I think that's a 3-pager. You see how all of that ties in. But that's your activity. It should be pretty fast, okay? It's just very tedious. So if you guys have questions, this will be due Sunday. You guys should be able to whip this out this evening if you have time. Again, the concepts are not difficult. It's just a very tedious problem. So if you have questions, go ahead and unmute yourself and you can ask, or you can put it in the chat room. And if not, then I'll be in Canvas Friday if you have questions. Otherwise, we're done for today.
Excuse me, Professor. I have a question.
Sure.
So for finding all the values that we need for the calculation for this experiment, should we just refer to Appendix 11 in the thermodynamic quantities in lab manual?
Let me show you where that it's better. Yeah, you should do that, or you can just use, let me share this with you. We can go here. Just go to my website and download that equation page. And if you go to the equation page, then you can find it there. So remember, the equation page is found in Fog Links, and then just go to information and equation. This is Chem 201 page. And if you download this or just put it in your computer, you will find thermodynamics at the very end, and then you can use that. Okay, and that way it's consistent with my key. If you're using another source, another book, unfortunately, okay, one textbook might have a different value than another. So that's why I put that whole table in the lab manual and here. That way we're all consistent. But yeah, you use this instead. Okay. Any other questions that you guys might have?
Sorry, I have one more question. This one sounds, so some of these values are negative, some of them are positive, but it doesn't really matter that if they are on the reactant part or on the product part, they should keep their sign, and compared to those ones, then it's just going to arrange our calculation. Is that correct?
Yes, you take these values based on how they're written, and that's the value depending on whether it's reactant or product. And then when you calculate the reaction, you're taking those values that you find in this table, and you're either putting it in the left side, products minus reactant, but these are the enthalpy, free energy, and entropy values for these chemicals under standard state. And I think we're using all standard state conditions for this activity. So yeah, you're using these values, and notice that there are negative values for that, because the formation, that is when these chemicals, remember this is delta H formation. So when these chemicals are made from their elemental substance, then the negative tells you it actually releases energy. The positive tells you that it actually requires energy. So these values right here, okay, right here, this is based on magnesium metal plus oxygen gas going to manganese oxide solid. And when you do that, and you measure it using some sort of experiment, you find out that it releases a lot of heat. Okay, so I hope that answers your question. A little bit more than your question, but I wanted to give you that background. Any other questions you guys might have on that? If not, you guys have a good evening. Fire me an email.
Hey,
if
Professor.
You have. Yes, Daniel.
I was just going over the second group of questions.
Yeah.
For like an explanation of that, can we just say because it has the highest number of atoms?
Complexity would be it.
Oh, okay.
The greater the chemical formula, the more complex the chemical formula, then you would use that. Okay.
Okay.
The higher complexity for the chemical in terms of their molar mass or their formula or things like that, the greater the entropy. Yeah.
Okay. Thank you.
Okay. All right. All right, everybody. Have a good evening, and we'll see what the election turnout will be. Bye.